Hey there, everyone. My name is Ryan Schul. Welcome to my math and stats and data science and analytics channel and a couple other things too. I talk about deep learning and artificial intelligence and just run the whole gamut with this thing. Okay. Trying to be more general at the beginning. When I first created this thing, it was more very specialized, very, very specific. And I realized it was a very niche area. And basically, what I want to do was much, much, much bigger than just data science. Okay, data science is kind of fun, but it's one little teeny, 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 tiny, little itty bitty kind of thing, right? In the real world, there's a lot of stuff that goes on, kind of tangential to data science, but outside the sphere or the realm of data science. But I think it's so interesting, so I'm trying to bake in all these different concepts and these different theories and these um, different what methodologies, I guess you could call it. Okay, so in the narrative today, I want to talk about real-time anomaly detection, and we're going to focus on wind turbine sensors, and we're going to use Kafka for the real-time feeds. So Kafka is a great tool for any kind of consistent and persistent real-time data feeds. You can think of updating stock prices, right, from the NYSE, um, things like real-time purchases on Amazon, eBay, right? When you see the clock counting down until the auction is won, and eBay, I'm sure, is controlled by Kafka. I don't know for a fact, but I mean, I'm pretty sure because Kafka is very good at handling a broad spectrum of different things, and it scales up and it scales out very nicely. Okay, so I'm gonna take you through Kafka, and as a caveat. Um, or as a preamble here, like I'm not an expert with Kafka by any means. I've used it a couple of times in my life, so I'm learning as you're learning. We can learn in parallel together, okay? So anyways, I want to look at wind turbine data. I dealt with this a couple of years ago. I worked for a renewable energy company. The data that they got was really bizarre. Let's put it nicely. That's all I can say about that. I mean, you would get metrics that would come in like 24, 25, whatever. They couldn't even indicate was that miles per hour for the wind? Was that the angle of the blade that was spinning? And was it a US standard system or metric? Nobody knew what it was. So the data was basically useless. You couldn't even use it, right? And I kind of got mad. A couple other people got mad. Some people got fired over that. I mean, come on, you have to have some kind of standardization around the data. Like a metric system is metric and US standard is standard, right? Like if you tell me which is which, I can convert one into the other, or I can convert the other into this one. But they didn't even know what was what. Like some was US, some was metric, and they would go side by side, but you couldn't identify which was what. So, anyways, that was a giant, colossal waste of time, massive failure. Okay, I don't want to talk about that, but it was a great learning opportunity. So I learned what not to do. Don't mix metric with US standard, and you can't identify which is which. So we're not going to do that in this case today. I want to look at early fault detection, right, and try to prevent catastrophic failures, like I was just talking about, but their failure was on a different level. Turbines generate massive streaming data, right? So that's why we need this Kafka tool. Like Excel is not going to handle this. A database is not going to handle this, guys. You need like a real workhorse, a real powerful tool to be able to digest that data, right? Assimilate it, digest it, and regurgitate it when needed, right? So Kafka is going to do that for you seamlessly. A lot of these tools are not. Excel is going to fall down in 15 to 20 seconds. It's going to fail. It's not going to be able to keep up. A database, most of them out there aren't going to be able to keep up with the demand, right? You need a real system that really delivers a real solution. So that's what we're going to look at here. And also we want to support grid reliability and stability. There could be regulatory concerns and safety issues around this, right? Compliance requirements that we have to adhere to. Kafka enables full digital twin predictive models, and Kafka integrates with basically not a couple of systems, not a couple of systems, not a couple hundred systems. It integrates with everything that's out there, okay? So it's very flexible. Again, scalable up and out, right? So both ways. So I'm going to go ahead and run the data in my first cell here. So I did put together this code a couple days ago. I tested it, seemed to work okay. But again, I am a Kafka newbie, so well, let's learn together at the same time here. I can't give you all the nuggets about Kafka because I don't know. I'm just getting into this stuff. I've used it a few times and it's worked phenomenal. So I would definitely recommend it. I want to dive in deeper and get to learn the system a little bit better. So anyways, I just want to preface the whole um, the whole dialogue today by saying that hopefully this works. I think it will work. I think the code works. I'm still a little bit new to the whole Kafka scene, so I'm going to try to embrace that, get my arms around it, and try to harness the power here. Okay, so just like we need to harness the power of these wind turbines. Okay, so nicely then right there. So when I run this, I have the number of turbines. Okay, from 1 to 5. We have a start time and then number of periods. So 6 times 48, there's 48 hours in 1 minute increments. Okay, so we're constantly checking data, testing the wind speed, testing the power that the turbine is capable of generating, probably in terms of megawatts. I think we'll see that here. If it's not disclosed by default, it's usually megawatts. Could be gigawatts, that's much bigger, but usually most of these systems generate capacities in terms of megawatts. Okay, so we're going to look at things like wind speed, and then RPM, which is rotations per minute. So this is the wind speed times 8 divided by this range. Okay, we're going to look at a normal range and iterate through these different variables within the range. So we have power in terms of kilowatts, okay? And then we're going to end up with turbine ID. So we have to identify these things, okay? If you have a turbine that's generating power and you don't know where it's coming from, I would say you got to pause right there, hit the pause button and figure that out. Okay, these things have to be identified. If you're just generating a lot of power and consuming a lot of power, or ingesting a lot of power and then selling that out to your customer base, but you don't know which turbines are generating what power, it's a recipe for disaster, right? So I understand like IDs are very important. We never do machine learning or data science based on the ID because has nothing to do with like the generating capacity of a turbine or any kind of asset, a hydro asset or a solar asset. Has nothing to do with that, right? But you just want to be able to identify, okay? You want to say, this is turbine 1, this is number 2, this is number 3, 4, 5, 6, 7, 8, 9, 10. You can even give them names, okay? A name like Fred or whatever, Dennis or Bill, something like that. As long as they're identifiable, right? You just have to have some identifier. We are going to use the timestamp, wind speed, RPMs, power in terms of kilowatts, right? Usually kilowatts is the preferred metric here. Although if you have a massive system like a massive hydro asset or a large nuclear power plant, it could easily be measured in terms of gigawatts, which is 1,000 kilowatts, right? So temperature, gearbox, and is anomaly. So that's what we're going to try to test for here. So this is what the data frame looks like. Okay, and I see some errors over here. I think I know why. So it's looking for Kafka already, right? We'll come back to this in 1 minute. All I wanted to do was just create the data frame. Let me just, again, is actually looking for Kafka at the first step here. And they disabled warnings over here. We shouldn't see too many warnings over here. Yeah, that's fine. I think that was just some random thing. Okay, so there's no warnings here. There's nothing to be concerned about. So we're gonna, oh, there is actually. Error thread Kafka produces network thread Kafka. Let me look at one thing real quick. Is it actually in this cell? Because I'm trying to figure out what's triggering this thing here. Okay, so that's 1. There's nothing in there. Okay. Let's see where it's coming from. Well, I don't know. I just say that's a non-issue. I don't think that's anything. Anyways, so this is what we have here. Timestamp, wind speed, RPM, rotation per minute, kilowatts, vibration, temperature of the gearbox, right? As the wind is spinning the turbine, right? It's generating power and it's generating friction as well. And the friction is going to increase the temperature inside that gearbox. And that actually could cause an anomaly, right? So there's a few things that could cause anomalies. We'll see that in just a minute. And then we're testing for whether or not is this an anomaly. That's what we're going to try to predict using a couple machine learning techniques over here, okay? So we want to look at the minute throughout the day and then the day of the week, the baseline mask and the marcher mask and the mask icing, okay? So in many instances, there's going to be no icing. However, if you are in the colder months in the northern part of North America, probably down in Texas, I would think it's pretty safe. Although even Texas has snow and ice sometimes, and that could create an anomaly too. So we're just going to stick it in there as a placeholder. There could be some icing issues and some conditions around icing, and that could create an anomaly. So if it does, we'll pick it up. Mask bearing, again, could be anomalous. We don't know for sure. We're going to prepare for this kind of event and just set up like a placeholder in case it occurs. We can capture it. Okay, and then mask overspeed, again, if the turbine is spinning too fast, that can create an anomaly too, and it could create the gearbox to heat up and maybe, like not implode, but what would be the term? Maybe kind of wear itself out. Like a higher friction rate could cause like increased severity of wear out or accelerated wear out of the part, right? So that could be another anomalous event that could eventually impair the asset, the wind turbine asset. So let me hit Control Enter over here just to run this. Okay, so we have timestamp, wind speed. What we had before is anomaly, and then the minute during the day. So you can see this is 0 minute, 1 minute, 2 minute, 3 minutes, 4 minutes. Okay, we're just looking at the head, and this is day 1. And if I do this again and look at the tail, we can see towards the end what's happening. Right, the head is the first 5 rows of the data frame, and the tail is the last 5 by default. And if you put a number in over here like 100, it would show the last 100 rows. Okay, so that's fine. Minute during the day. This is day 1 and day 2. So we're looking at 48 hours. Remember, so all day 48 hours, and this is the minute throughout the day. Okay, so we have a 2-day cycle or 24-hour cycle, whatever you want to call it. So let's look at some feature engineering exercises right now and try to create some additional features from the features that pre-exist in our data frame right now. Okay, we want to create some new features to try to understand the nuances and not motion, the action of this wind turbine and how it's going to change throughout the course of the day and over the course of 2 days. So in the number of turbines that we have 5 here. We're going to look at minutes, turbine ID, it's power, kilowatts, and then we're going to go down here and look at, again, the turbine ID and the wind speed. We're going to use lambda right here, a lambda function. I have a whole video on my channel about lambda functions and how basically a lambda function will perform essentially like a loop. It's kind of like an alternative to using a loop. In some cases, it might actually perform better. The performance might outperform what a loop would do. And in some cases, it's just neater to write the language. If you can do a lambda function all in one line, if you look at this close, it's actually one line. If I pull this over, and that is contained within the parentheses over here. So it's a one-liner rather than looping through different elements in our data frame or in our list, or you can loop through elements in dictionary, a bunch of different data types, right? We can do everything on one single line without the loop. So it basically replaces a loop or acts so it's a substitute for a loop, right? So we have the power in kilowatts minus expected power. This is going to be residual power, so whatever's left over. And we have vibration and temperature. So we have all the elements here that we need to go ahead and put this into a big mixing bowl and mix it up and see what the recipe comes out like, right? We'll see how things shake out. Imagine this as a big mixing bowl, and these are the ingredients right here. We're going to dump it in, mix it up, and we're going to see what the output is. So again, we have wind speed, power, vibration, gearbox temperature. So the usual suspects that we saw above, and I have the feature columns. This is a list, and I'm going to go ahead and put the feature columns over here, Control F, and you can see is anomaly head. So this is actually a list, and we're going to look at all these features and try to understand the power output, which is constant times the wind speed. Okay, we want to know the expected power. During icing, if there's an anomalous event like icing, that's not going to happen too often. But if it does, what kind of impact is that going to have on the wind turbine? And how is that going to affect the performance of our asset? These are called assets, right? Because it's worth something. There's a tangible intrinsic value in this tangible object, right? So we want to understand what the impact on the performance is. So large negative residual or large positive residual. Remember, the residual is the power minus the kilowatts minus the expected power, right? So it's always like a maximum kilowatt output. It could be maybe 10 megawatts, maybe 11, 12, maybe up to 15, something like that. It could be a little higher, a little lower. But we want to understand the maximum output minus the expected. If the wind isn't blowing too hard, then the expected output is going to be a little bit less, right? If it's blowing pretty strong, the expected output is going to be quite a bit more up to a certain limit, right? As the wind blows more and more and more, the asset can only output a certain amount of kilowatts in terms of energy that we can harness and we can sell to our customer base, right? You can't go beyond the threshold of the asset and what it's capable of producing, right? Okay, so we have the data frame down here, expected power and expected residual. Okay, so that looks good, vibration and the temperature. And if you look closely, we are appending all of this into the data frame that we had before. So if I go data frame ahead, if I go Control F and search for data frame, so this is appended onto the data frame right here, right? So data frame location, vibration Z comes from here, vibration minus mean divided by the standard deviation plus 1 to the power of 6. So this is what, 1 million, right? And then location, temperature, gearbox minus the mean divided by the temperature plus 1 to the million, right? Or 1 million. So this is basically just taking everything and just normalizing all the data that we're going to analyze and append to the data frame. So now we're up to this step. This is looking pretty good at this point. So we have the database base and the database monitor, okay? And then we have the XBase and the XBase monitor. So we're going to actually use this machine learning algorithm called isolation forest. I have a couple videos on my channel that speak specifically to this type of anomaly detection sort of logic. And there's several other ways to do this. I like this isolation forest. It's pretty robust. I think it does a good job overall. It's pretty easy to understand what it's doing under the hood and to take that and communicate that to stakeholders or to other people that need to have this knowledge, and we can share our information with other people pretty easily. Some of these machine learning algorithms are really black boxes, and it's very hard to understand. When you look at the inputs and you look at the outputs, you can say, yes, I think this makes sense based on my knowledge of this discipline, of this area, based on my knowledge of how wind turbines work. I can understand the inputs, I can understand the outputs, and I can see how they're connected together, right? So, but you have to have faith in the black box, right? If you're working with that. This isolation forest is not super hard to understand, right? So it is a little bit of a black box, but not really. It's pretty easy to understand what goes in, what happens in between, under the hood, and what comes out. So I like to work with this one a lot. I've got a couple of videos on my channel. If you feel motivated, go ahead and search for that and check it out. So now let me go ahead and run this. Okay, I'm getting power residual vibration temp Z. Did I not do this? I thought I just did this. Let me see here. Let me check this out here. Yeah, that looks fine. I don't know. Sometimes this computer does weird things. You have to hit the run button twice or control enter to run the cell, right? That refreshes the cell. You can do that. Or hit this little play button over here or go over here to run selected cell. So control enter is the shortcut for that. Sometimes, I don't know if it's gremlins or what. I write the code, everything runs fast. I turn on the recorder and try to do the demo and start my whole narrative. I would call this part the narrative. And then the code just breaks and just fails. And then you do it the second time, then it works, right? So one time it doesn't work, 2 times it works. I don't know why, but it's something going on. But maybe for Christmas I'll get a new ThinkPad. This one is just about ready to be put out to pasture. And we're getting close to Christmas. Today is actually Thanksgiving in the United States. So 11/27/2025. Happy Thanksgiving to all the turkey eaters out there. And if you're not eating turkey, then happy Thursday to you. Okay, so just normal day, unless you're in the United States, and that's Thanksgiving. So we have everything we need at this point for our data frame. We have the RPMs, the power. Is this anomaly? 0 is no, 1 is yes. So it's always binary, yes or no. On or off, true or false, 0 or 1. So 1 is yes or on, and 0 or 0, I guess, is off or no, right? So that's it. So we have the expected power residual, vibration, temperature, and anomaly score, okay? So this all comes from the ISO. So over here we have isolation forest. We are defining that model as this. ISO score takes X mon. So this is the monitor of feature columns. And remember, these are the feature columns over here. So these are all the features in our data set, and these are all the columns that comprise the feature data set. So you take everything from xmon, or which are just the values of the feature columns. We feed that into isolation score. It's going to go ahead and assign a score. This is called anomaly score or anom score. We're abbreviating it just to be kind of cool and kind of sexy or whatever you want to call it. That's my anom score. So we set a threshold. So anything below the base scores of 99th percentile of normal can pass the threshold. Okay, and we can see the threshold down here is 0.571. Okay, so anything greater than that is going to be picked up over here, and that threshold comes over here, anomaly score, and that goes down to, let me see something here. Where's it flow to? Oh, the head and tail. Okay, so that's just the data frame, and the threshold is set over here. So anything that's a base score has to be under 0.571. Anything greater than that is going to be an anomaly territory, right? So it's greater than the base. The base is just going to be the fundamental, the baseline, the average. Anything greater than that is going to be considered anomaly. Okay, so let me turn that off. It's a little bit hard to read. So anomaly score greater than threshold is flagged. And we have turbine ID. I want to take a quick look at this. Let me display that. I'll keep the classifier right there. Go ahead. I want to take a look at this. So we have is flagged and turbine ID. Is flagged, no. And I see, is flagged. That's the only thing that we add to the data frame right here. And these are all under, right? So where is the anomaly score? 0.42, 442, 442. If I do this over here and look at the tail, I just wanted to see if I can find a couple that have anomalies. And no, I can go bigger though. I can go to 100. Okay, so, oh, and then we have that thing coming over. Okay, so I might have to modify this just a bit. Let me look at this thing over here. I have another piece of code that I wanted to look at. Okay, that's fine. Let me copy and paste this over here. Yeah, put that in. That's my pandas data frame. That will give me everything of the last 100 rows, and I can expand this too. Okay, I was just looking for anomalies. I don't see too many, but I think that's okay because anomalies are pretty rare anyways. That's why it's considered an anomaly. You're not going to find too many that come up and impact the performance of this asset. Let me look at one more view here. All right, that is by definition an anomaly, something that is an outlier. It's extreme. It's an unusual event. Certainly an icing situation that could take out the turbine or cause it to create a lot of friction, and cause heating within the gearbox or something like that. That could be detrimental to the operations of the overall performance of the asset. And I didn't see anything here, but that's fine. Again, anomalies are going to be pretty rare. You're not going to see too many. So if we see one, we'll just identify it, we'll flag it, and we'll measure that and recognize that. But I don't see anything here. So let me go back to 5 head and tail. That's fine. Okay. And you can see that the model is performing pretty well here. So we have a precision of 0.97, recall 0.99, so very high. Higher is better. Close to 1.0 is great. We're at 0.97, 0.99, so we're at a good spot right now. F1 score 0.98. So these are the anomalies. Anything that is 0, if the model is performing well, I'd like to see close to 1.0 or high 0.9. So I see 98, 99, 97, that's fine. These are the anomalies. Again, you're not going to see too many of these, so I would expect a precision recall and F1 score to be lower because the model only sees a handful of these anomalies. It's hard for it to understand what is an anomaly, what causes this event, how do we measure this event, and how do we calculate the precision, the recall, and the F1 score if you only see a few of these events, right? It's kind of hard for them all to learn because most of the time, probably 95, maybe 97, 98, maybe even 99% of the time, there is no anomaly, right? These are outliers. These are unusual, weird events that are way beyond what a normal event would be. So very, very high peak or very, very low valley, those would be picked up as anomalies. But again, most of the time, you're going to have pretty standard kilowatt power generation, daytime, night. Now the wind could blow harder and generate more power. Maybe it doesn't blow quite as hard and generates less power, but you're not going to have like these giant spikes all the time, or they wouldn't be anomalies. That would be a common event, right? So I'd expect the precision recall and F1 score by the definition of anomaly to be less because the model doesn't see too many of these, and it's very hard to learn. If you see white swans everywhere and there's hundreds or thousands or 10,000 white swans, all of a sudden you see a black one, it's still a swan, right? It's just a black swan. But if you tell a child, hey, that's a black swan, they'll be like, what are you talking about? Like swans are white, right? And even an adult, maybe you've never seen a black swan. I can't even say I've seen one in my life. I've seen pictures and I've seen like little illustrations, drawings and cartoons, but I don't know if I've ever seen a black swan. But regardless, it is still a swan, but seeing one would be kind of indicative of an anomaly event, right? That would be sort of an anomaly because there's not too many of these things, but they still exist, but you just don't encounter it too often. So anyways, I'm not going to go off on a huge tangent there. We have a list called alerts, right? Here's the list defined by 2 square brackets. I'm going to append this, the contents of this data type, which is a dictionary. You can tell by the curly braces. This has a little curly brace. If I zoom in there, you can see kind of the curl over there. You see that? It's curled right there. That is the shift key, and just above the enter and the quotation, the double quotation on the keyboard, right? And this over here is a list. It has just square brackets, right? So we're going to take everything and append it from the dictionary into the list. So if you see my other videos, I do this all the time. I love lists because they are mutable. You can change them. You can append. You can slice and dice and do everything you want with a tuple. You cannot append, right? These are mutable. You can copy a tuple and truncate it and cut out parts of a tuple and create a new tuple from an existing tuple, but I think they're very cumbersome to work with. I don't think there's a real practical reason to use tuples. I almost never use it. I think less than 1% of the time I use it. Usually dictionaries, that's what we have here. This shows a key value pair. Here's the key. Here's the value on the right-hand side. It's always separated by the colon. Or a list. I love working with lists. Or a data frame. I use these 3 ad nauseum, like all the time in all my videos. I can't remember the last time I've used a tuple, if ever. So here's my alerts. So here's the 5 wind turbines. We start with 0 and go up to 4. And these are turbine by ID. The mean anomaly. Okay, so these 2 have no anomalies. This would be the average. And these actually have higher degrees of anomalies, right? This is actually the highest, 0.937. So turbine 1, there's something going on over there. And even over here, if the mean of all anomalies is 0.90, and these down here is 0. So these turbines right here have no issue. This one has had a few issues, and these 2 are kind of plagued with issues, right? So we have to jump in there and see what's going on here and do some additional analysis. So we have the turbine ID. Is anomaly 0? No, that matches this one over here, or matches the first item over here. So location 0, wind speed 7 miles per hour, rotation 51 knots, I think. This is 269 kilowatts, so generate pretty decent power there. Power residual, remember we defined that as, let me get that over there. What was the definition? Whoops. Okay. And if we go up here, we said the residual was kilowatts power minus expected power. I'm going to make a note of that because we'll probably come back to that. Residual is expected power kilowatts minus expected power. So here we go. Equal power W minus power. Okay. So for the rest of the narrative here, that is going to be the definition of residual power. Okay, let's go back to where we were before. I think this is a spot. No, we did the precision recall. That is good. Okay, so this is where we left off. DF classify root cause. So I'm creating a UDF here. This is a user-defined function. We were looking at the power residual. Is this less than negative 200 of the row speed? Oh, less than 200 and the wind speed greater than 5. Okay, so we said power residual is power kilowatts minus expected power and the wind speed is greater than 5 miles per hour. So if we fit within this definition, within this band here, power loss versus wind is possible icing or fouling, right? So the residual power, we said, is power kilowatts minus expected power. So it's actually negative, but the wind speed is positive. That seems weird, right? Like if the wind is blowing on this guy, this turbine, and it's supposed to be generating power, but it's generating less than 200, the residual is actually negative. That tells me there's icing or there's something impeding with the flow of the power, which comes from the spinning of the turbine, of the blade, right? So something is slowing it down, probably icing, maybe even, I don't know what else it would be. Maybe I was thinking like a big goose or a black swan. That would be kind of crazy. If a black swan flew into the turbine and it got stuck or something, maybe that would be like, that is a black swan event. If I've ever seen one, if I've ever heard of that before, probably icing. You can say it's probably icing. So if the vibration is greater than 3 and temperature greater than 3, vibration spike and temperature spike, probably gearbox fault. Okay, so we're trying to come up with a couple of definitions and define these, right, as a root cause tag. So we're defining RPM also greater than 180 and wind speed less than 10. This is overspeed condition, so that could lead to some kind of burnout or some kind of high friction event that could cause damage to the asset, something like that, right? So we're trying to define based on the conditions, right? The wind speed, the power that is generating, the speed or the temperature or the vibration of the gearbox, and then the wind speed versus RPM. That could be an overspeed condition, right? So we're trying to define these different criteria and append that into the data frame right here. So that becomes return anomaly. Okay, so this anomaly, classify root cause. This is classify root cause, and we're assigning that to this feature in the data frame, or this column in the data frame. A column in the feature is the same thing, right? So if those conditions are true, that's what's happening, and we're looking at the first 15 records in that data frame. Okay, so hopefully that makes sense. Now let's take a look and visualize what's actually happening here. We are going to go ahead and create a Plotly chart. I like these Plotly charts a lot. It's interactive, it's dynamic. You can zoom in, you can zoom out. You put your mouse over it, and you have a little pop-up, or a tooltip it's called, and it pops up like a kind of like a cartoon on the image here, on the graph. Okay, so here we have the wind speed and the power generated from the turbine asset over a period of time. Let me get this back. I don't know why that shrank down. So you have January 1, 24-hour period, January 2, 24-hour period. I only have 2 days, but it should illustrate the point pretty nicely. So at the beginning of the day, this is midnight, 1, 2, 3 o'clock in the morning, 4, 5, 6 o'clock, 7 o'clock, 8, 11 a.m., 12, this is noon. Now 1700 to 8 p.m., 9, this is like midnight. Okay, this is midnight and time 2. So you can see the wind kind of picks up overnight, 4 or 5 o'clock in the morning, dies down a little bit earlier, a little bit later in the morning. Early afternoon kind of dips down, hits the low point over here, and then kind of ramps up again. Now we have an anomaly, right? So this goes offline. If we zoom in, we can see the details here. The asset is trying to pick up signals, right? And generate those signals and send it to our Kafka, our Kafka solution here that's going to capture all these signals, but it went offline, so Kafka can't capture this, right? So we have a disruption in the data that's being provided to us. That's this straight kind of angled line going down. You can see the trend is going down, and it kind of like goes into a valley and then peaks up again the next day. But when we're offline, we can't get any data. So here's another example over here. So this is more steady and continuous. This is vibration over here, was wind speed, right? Power in kilowatts, which is directly relative to wind speed. So power or wind speed, they're going to be very synonymous with each other, high correlation there. Vibration, we want to see very low vibration, which is the case over here, except when we went offline. All right, this is about 12 p.m. to 6 p.m. day 2. So this is January 2, 2023. This is about 6 a.m. to 12 p.m. This is turbine 0. So turbine 0 had an issue. Turbine 1 had an issue. Turbine 2 had an issue over here, right? They have an anomaly around, this is 1900, 2000. This is around 8 p.m. until about 11 p.m. They had an issue. So there's more anomalies, right? This is RPM with anomalies. Before that, we saw vibration, and before that was power. Okay, if we go back over here, what was I going to look at? So we had 1, 2, and 3, right? Oh, this is T0, 1, 2, and I'm sorry, T0, T1, and T2. So this was the anomaly T0, T1, and T2 is right there. And T3 and T4 had no issues, right? So no icing, no discontinuity with the vibration, and no issues with the RPM. Okay, here we had a pause in kilowatt hours at least being recorded. Okay, the asset could still be generating power and delivering power, but we didn't capture that. We didn't record what was happening. This was the vibration, I think, was number 1 or number 2 actually. We start with 0, so it's 1. This is 2, even though it says 1. And this is RPM, I think, for T2. So if we go down here, we'll see essentially the same thing. Here's T0, okay? T1 is right there, second anomaly, T2, and T3 and T4 had no anomalies, so they are fine, okay? Let's go over here, revisit this again. So we're going to use another isolation forest technique. And again, we're looking for anomalies. That's what this is great for, right? So there's a few different ways to do it. Again, I'm a big fan of IF, isolation forest. IF is the abbreviation. So we're going to implement this again. In fact, that might be a good video, like comparing the different anomaly detection algorithms in Python, right? Pretty much are all scikit-learn libraries, right? You can see scikit-learn right here. That might be a good video. Let me see. Compare and contrast. And contrast. Anomaly. Algos. Okay, so that is a good idea for another video. Maybe I'll do that sometime in the next few days. I did one comparing all the regression algorithms. I did one comparing all the classification algorithms. Both came out good. I did one comparing all the clustering algorithms and using different metrics to compare the performance of each clustering algorithm. If you're interested in that, take a look. That's on the channel. That came out a couple months ago. I was pretty happy with the output from that one. So let's get back into this isolation forest. We have the training and the testing. All right, we split it into training and testing. So we have 2 groups. I'm not going to get into the whole backstory. This is all machine learning data science 101. I have several videos, dozens on my channel that talk about this. I'm not going to get into it. But these are the training pieces of the model right here. This is the testing piece, and this is what we're trying to predict, right? So these are the independent variables, train test. If you go over here, you can see this in a nice view right here. Okay, anything that is not anomaly. So this would be all training, and then this over here. Can I actually go between these or not? It's not letting me. Okay, so everything highlighted here except for is anomaly is an independent variable. We're trying to predict anomalies. So that is the dependent variable. It's dependent on the independent variables, okay? So hopefully that makes sense. So we have the isolation forest, okay? That goes into our model. We define it right there, ISO. If I go down here, we go ahead and feed in the X test to predict ISO predict X test. This is the Y predict ISO, right? Isolation forest. And that goes down here. If it is 1, this is Y predict. Okay, and this is how we define anomaly, okay? So take a look at that, pause the video right here. If that doesn't totally make sense, it's okay. First time I looked at it, I was like, what the hell are you talking about? I don't understand what this is. But Google it, use ChatGPT. It's gonna make sense pretty quick, I promise you that, okay? This is how you set up, this is how you execute. So I'm not gonna give you the whole backstory of everything. That would take hours and hours. I just wanna show you the code, show you how everything works. I'll share all this code with you so you can copy and paste it into your own Jupyter Notebook environment and run it right out of the box. Just drop it in, run it, and you are good to go. But I'm not going to go back and explain every single nuance of every single thing. It's going to take hours and hours, and I think I'm going to lose 99% of the audience if I do that. If you understand, move on. If you don't, hit the pause button right now. Do a little research just so it makes sense, and then continue on. So we have the classification report. Here's the non-anomalies, right? So most of the cases are not anomalies. They could just be normal, business as usual, BAU processes, right? This is an anomaly. We don't have quite so many records or incidents So we don't know exactly what this looks like because this could be 1 in 100, 1 in 200, maybe 1 in 50, right? But if we have 50 records and we measure, okay, this is not anomaly. I know what the inputs look like. I know what the outputs look like. I can understand this. Then all of a sudden an anomaly pops up. It's a little bit harder for the model to understand this because it's so rare. It doesn't come up a lot. And the model is just struggling just to figure out what the heck is this thing, right? But it tries to make sense of it and bake that into the whole classification report. So typically, the anomalies or the ones or whatever this is, something that's true is rare. So it's harder for the model to learn this. Now you can use different techniques, SMOT and oversample from the underrepresented population. That's what this is. And you can undersample from the overrepresented population. That's what that is. So you can do that. I'm not going to get into that whole thing at this point. I'm just going to move on here. So now we have a SHAP analysis. So SHAP is pretty nice because it basically shows you how the model is performing and why the model performs this way. So it really exposes everything under the hood and answers the question, why is this happening? So in my experience, I've been on Wall Street for 20 years, I think why something happens is the most important thing that you need to know, right? And this is the most important question that you can ask. Why is this happening? You can see what happened. I can see exactly what happened. I see what happens right here, right? I know what happened. I can see it. I know when it happened. I saw the first 2 days of the year, January 1st, January 2nd. I know how it happened. I know when it happened, where it happened, right? I don't really know why it happened until I get to this point right here, run this SHAP model, and this is going to tell me why these things are happening. So I think personally, the why is the most important thing for me and for most of the people I work with. Most of the stakeholders are saying, why is this happening? Like, I need to know why this happened. The what, the where, the when, the how, which, wherever. Like, these questions are pretty obvious. It just it's all given to you, right? You just have to read the code over here. It's right above here. But there's nothing that tells you why this happens until you run one of these SHAP reports. Or there's a couple ways to do this. This is one of my preferred ways to do it. There's another. About the other one. But I think this is the better of the two. But there's a couple different approaches to solving this problem of why. So we see the different features over here: the temperature Z, vibration, RPM, vibration, wind speed. If we go back over here just a little bit, you'll see all these features in the data frame over here. Okay, so wind speed, RPM, power, temperature, gearbox, right? So that is just measuring all the different features, and it's going to tell us what's going on here, right? So we peel back the layers of complexity, look inside of this onion, right? An onion has a lot of different layers, or open up the hood of this machine learning algorithm and see what's under the hood here. So we can pick one strongly anomalous point and add anomaly score to a copy from the original features, okay? So we want to monitor X and look at the anomaly score. For X, SHAP equals X monitor feature columns, and we have monitor location. Top indices, IDX is the index, right? The index is basically just the number of rows. Start with 0, go down to n number of rows, whatever you have, 2,000 or 20,000 or 2 million. We go from 0 to the end, and the feature columns. So we're going to force a plot of this SHAP model right here. SHAP, if you go back and look here, you'll see that user over here. This is called import SHAP. That's what we're looking at. And basically, it tells us right here, 5.46 is on the left. So this is the predicted score for this observation, okay? So for temperature Z, we are looking at 28.3. The power residual is 87.9. The vibration is 0.58. Power in terms of kilowatts is 124.2. They're kind of mixed in here a little bit, kind of overlaid, but I have the details broken out down here. And the temperature of the gearbox is about 60.5. Okay, we can say that's Fahrenheit. It doesn't directly say, but that's the implication here. So bars pointing to the right, push the predictions upward towards more of whatever you're predicting. We're trying to predict anomalies, right? The more anomalous, the more to the right, and the more right leaning the model is. If the model is an output anomaly score or high probability, right? We look at the bars pointing to the left, and it pushes the prediction down. So if it goes to the left, it's down, up to the right. And if it's down more normal and lower probability of an anomaly, right? So right to the right, more anomaly, to the left, less anomaly. The color indicates what feature value is actually low relative to the data set. So red is high and blue is low. So if you look over here, you should see more red dots. They kind of get mixed in. It looks a little bit purple, but more red to the right and high. And this is more of an anomaly. More blue to the left, less to the red. And it's dragging us down and saying more not anomaly, more standard operating procedure, business as usual, right? Long bar means the feature had a big impact on the moving of the prediction away from the baseline, and a short bar just means it doesn't have that much of an impact. So if you look over here, wind speed vibration doesn't have that much of an impact on anomaly. Temperature does, right? So the temperature can cause a lot of friction in the gearbox and cause it to either disintegrate at an accelerated rate. Maybe the gearbox could last 5, 6, 7 years. I'm not sure what the life is, but if it heats up to a supernormal level, the lifespan is going to be shortened, and that is going to cause more vibrations, right? And more of an anomalous event, more anomalies, more heat, and more maybe vibrations, more shaking, or less power delivery. Even if the wind is increasing, maybe the power in terms of kilowatts that's captured and delivered to our customer base is lower. So temperature clearly has a higher influence on anomalies. The gearbox, to some extent, power residual, a little bit vibration, a little bit RPM, a little bit, but to a lesser extent, right? The longer the line here, the more influence it has on an anomaly event, and the shorter line, the less influence, right? So this is why these things happen. This is why we have anomalies, because of the temperature. What else is along? The power residual is going to cause anomalous events, and RPM and power in terms of kilowatts is kind of the same, and vibration is kind of the same there. But wind speed doesn't really cause anomalies, and temperature, the gearbox, doesn't really cause anomalies either. Okay, so we got that out of the way, so that looks good. So at this point, I'm going to start up my Kafka tool here, and I'm going to give you all this code again. You can go online, you can Google this, you can go on ChatGPT, and you'll probably get essentially the same recommendation here. We have to start Zookeeper, and this is how you do it. So you have to go to your C prompt. I have a couple open up right here that I was playing around with earlier, not later. How could it be later? So it was in the past. Earlier today. So I'm going to put that in, just copy and paste it. Once you've downloaded Kafka, you can just Google it, just look for Kafka install. It's pretty easy to download and set up. I have Windows. Make sure you get the right type. If you have Mac, you have to get Mac. If you have Windows, you get Windows, right? If I go over here, probably you can find it. Just a couple of seconds here. So Google. Yeah, Windows. I have Windows. I've never understood those Mac machines. Last time I used one, I think was 1997, and I haven't touched it since. So support releases, download Kafka. It looks like this button in the upper right-hand corner will probably do it. And there's some notes and some releases over here. Okay, so just go ahead and Google for that, download it, install it. And then let me go back to my C prompt over here, and it's started up. Okay, so the first one is started. Now, this isn't complicated, but just pay attention here. There's 3 Kafka, bare minimum 2, but to test to make sure it's running, there's really 3 steps here. So that's the first step. The second one, again, C prompt, you want to make sure it says C Windows System at the top. I also have an Anaconda prompt over here. If you look closely, here's my Anaconda. So here's Anaconda prompt, right? It looks kind of like the C prompt, but look in the upper left-hand corner. If it says Anaconda prompt, you cannot run Kafka there, okay? It's not going to work. It's going to cause an error, or you get some weird stuff, and it's not going to make any sense. So make sure you go to the C prompt to install this. If you do a pip install, pip, or any Python library. Now, what was that? It didn't even go on the line, sorry. Wait a second. What's this thing doing? Let me hit. So if you're installing any kind of Python library, that's how you do it, right? But you have to be in the Anaconda prompt if you're doing some kind of Python work. So Kafka has really nothing to do with Anaconda or Python. All it is like a real-time system that captures information, packets of data, and ingests it and digests it, and then regurgitates it and spits it out and does whatever you tell it to do, right? But it's like always processing the information. It's always going. It's never up. It's never down. Hopefully, if it crashes, you can have a a couple of ways to automatically reboot it. You can test to make sure Kafka is running. If it does go down somehow, that would be unusual because it's highly reliable, 99.99999% of the time it's up or whatever. If it does go down, you can set like a little tool that tests the connection. If it's down, that restarts it automatically, or whatever. You can have backups and fail-safe things like that, right? But most of the time, this is up capturing information. So you can imagine it's like a data center, always running, always on, just going. That's what Kafka is. A server machine that is serving information to the client. The client is you and me, the end user, or the laptop. I have a laptop. That would be a client. The laptop can actually be a server too. If your laptop is on and you have a website on your laptop, as long as you don't shut down the laptop, people can literally log into your laptop like a server, and that's always on. So you can think of Kafka like that. It's always on, always running, always processing information, okay? So there's two things that we have to run, Zookeeper and in another window, the Kafka broker. Now, just to make sure this is actually running over here, we can do this right here, cd Kafka. This is the I don't know what this is. It looks like an IP address. I don't know if it's called Kafka IP or what, but I Googled this and it does work. So if I copy and paste this, it's just going to show you of what has been set up before and if anything is running right now. So you can see it right there, right? Oh, I see. It has to go there. That is the location. And then I need this. Okay, so it runs in port 9092. Again, so I apologize for this a little bit, but I'm just learning this stuff too, guys. So I'm sharing my knowledge with you as I go. So bin Windows Kafka. And we should see a list of a couple Kafka instances I spun up recently and did a little work on. You can see this for. So credit card transactions. I was not parsing, but working on some credit card transactions, raw flows, stock prices, and then turbine sensors. That's what we're doing right now today. So that's it. So you copy and paste this into one window from the C to the end. Second C prompt window, make sure it's not Anaconda, from the C to the end, and then bin right here. I'll put a little space. Maybe that is the precursor, right? So you hit CD to get back to the original base location, and then you put this in, and then you would put that in. I guess I'll leave that. I think it makes a little more sense. Okay, let's move on. We are 52 minutes. I try to keep these videos kind of short. It doesn't always work out the way I think it will. So we have turbine ID, wind speed, and vibration. So I'm running this. This is the next step here. We're looking for localhost 9092. This is the port that it runs on. So I have two instances of Kafka running. The broker, right, and Zookeeper. So the Zookeeper is number one. Kafka broker is number two. And it says finish streaming turbine data. So it just ingested all the data, just looked for everything that I sent to it, and it's still up and running. Everything is fine. Okay, as long as you don't see it stopping over here, you can assume everything is running, and this is fine. I'm just looking at the lists of Kafka jobs I ran before, so that's fine. Okay, so we're going to build and save the isolation forest, and we're going to go ahead and pickle it. Okay, so we're going to save this as an ISO model turbine pickle. Go enter to run, and let me take a pause for a second here. Alrighty then, I'm going to have to finish this up before my son gets super restless and this video is never going to end. So let me run this right here, Control Enter. Okay, and open up this part right here where everything gets saved. So with this, you have to go where your default Anaconda is installed. Mine is installed right over here. So if I go here, it's actually, that's not really it. Go here. And if I look at the properties, it goes C users and then my name, Brian _. Okay, so that is where this goes back to. That one looks a little bit weird because it should say the whole path over there, but it doesn't. Oh, it's like this and go back one level, I think. Okay, so this is it. Anyways, you go where your Anaconda saves to default. Okay, so I'm looking for ISO model turbine pickle. That is right here. Okay, and then saved. Oh, it just says, it just prints it out over here. So this is what it saves as a pickled file. And it prints it out there. Okay, so it saved ISO model turbine expected power coefficients pickle. Okay, so go back over here. So expected power coefficients pickle, and the last one is vibration template baseline pickle, and that is right here. So I think this is a hilarious term. It's called pickling the file. I don't know the exact history. I never even studied Python school. I just read some books and just learned all hands-on. So I don't know all all of the details of everything here. There's definitely gaps in my knowledge, but I guess it's called a pickle because if you take a cucumber and you pickle it, it's preserved for some time in the future, and then if you like pickles, you can go ahead and eat the pickle after the cucumber manifests into a pickle, right? So I think this is kind of the same thing. You train the model, it's been trained, tested, validated over here. Okay, if I go back up here, now I'm missing my white again. Oh my God, this thing just drives me nuts. It's time for a new computer, guys. It is time. It is past time for a new computer. Oh, so this thing has some wicked Alzheimer's here. It just keeps forgetting every single thing that it does. It just can't preserve anything in memory. What I want to show you is this. It's always so painful. I don't know why. This right here is a model, okay? It's been trained and tested. I guess it's just trying to tell me to hurry the heck up. We're 56 minutes, almost an hour into it. So the model's been trained, tested, right? Performing pretty well, high 0.9s, so I'm happy with that. So we're taking the model, literally saving the model, pickling it for some time in the future. That's all that means to me. I don't know the whole history or the orientation of the terminology, but that's what it means to me. So I can go ahead. I don't think I'm going to need that. I'm going to go ahead and run this next line over here. We should be good to go. I was testing something over here. I think I'll delete that. Okay, so it's doing the alert turbine testing, and it's going to go for, I think, 500 iterations, maximum messages 500. So it's still interacting with Kafka, right? So you have the broker and you have the zookeeper. Those are the two instances of Kafka that's running. Again, in real time, it's always running, processing, assimilating, digesting, regurgitating this information in real time, just like a server, like a data farm, like a laptop, like my laptop. If it's always on, always running, and you try to contact my laptop, you can, right? If you have the IP address, as long as it's turned on, you can. There's a little error over here. That looks a little bit weird. I could Google that or put that into ChatGPT, but I think it's fine. We processed 500 messages. It's probably a little bug or a little gremlin in there. I've got a lot on my computer. I'm not too worried about that. Pretty much it worked the way it was supposed to. I'm going to come back and delete that. I'm just going to go in here and make sure I do not need that thing. Okay, so the next step here, Control Enter. So we have rule, overspeed, a couple of the rules, hot, low, wind, the gearbox, the temperature, vibrations, right? Same thing that we saw before, so on and so forth. Control Enter. This thing is telling me to hurry up and finish up. And about 1 hour 57:55 into it, so I have 2 minutes to go. So here's the timestamp. Turbine ID is anomaly. No anomalies over here, so we look good. All right, no instances. Let me refresh this cell down here. Control Enter. So mostly non-anomalies, 6,660, 540 anomalies. That's okay. Again, that's friction in the gearbox, icing, vibration, something like that, something that's not normal. That is okay. We're just trying to pick it up, trying to detect it and report on that. Control, let me cut that out. I don't need that. That's really doing absolutely nothing. Control Enter to refresh this. And you can see in the plotly chart, we have true anomalies by count. This is injected anomaly, isolation force. This is machine learning. The number of rules we have is 333. These are all counts, right? Anomaly counts by detector type. And hybrid, either machine learning or rules. So if you have a business rule, this is just logic. If this, then this. If that, then this kind of thing. Machine learning is more based on statistics and much more sophisticated than any type of rule-based orientation, right? Okay, and then I think the last thing over here, just before we cross over the finish line, is a correlation map, right? So we have the wind speed and the RPM. These are going to be pretty highly correlated. The darker the color, the higher the correlation. Wind speed in kilowatts has 0.82 correlation, so high correlation, right? Vibration and vibration Z, these are almost perfect, right? Vibration is vibration. I think we only need one of these. We only need two. And temperature Z and vibration. So that is interesting. As the temperature increases, the vibration increases and vice versa. So these are highly correlated right here. These have no correlation. So power, vibration, power should be smooth, right? There should be zero correlation between power and vibration. Vibration Z, same thing. I think we can drop one of these. Temperature of the gearbox, there should be no correlation between power and the temp of the gearbox. Those should be well-oiled machines just spinning, generating power. If the power is increasing and vibration is increasing and temperature is increasing, that's a problem, right? So right now I think this is fine. Power, vibration, and temperature, all independent. Power and wind speed are highly correlated, so highly dependent. And RPM and wind speed, there is slight positive correlation, 0.52. Anything over 0.5, anything over 0.7 is considered statistically significant. So wind speed and RPM have a slight positive correlation, but no significant statistical correlation. But power and wind speed do have a statistical correlation, 0.82. Greater than 0.7 is statistically significant. This is a histogram showing you non-anomalies in blue and anomalies in red. So it's a little bit of overlap. The anomalies kind of spread out to the tail. That's kind of a black swan event, right? More frequent than black swan. Black swan is very rare. But you can see when you get further and further into the tail, maybe far over to the right could be a black swan event. These are just anomalies here. Anything in blue is not anomaly. This is business as usual. And here are the 5 turbines. T0, 1, 2, 3, and 4. Remember, it's 0 based, so I'll start with 0 and 4. We still have 5. So T0, this is the box plot, the distribution here. Vibrations 0.22, and the distribution here is 0.13. Here it's 0.2, but we have some outliers over here, 0.6 and 0.14, and then 0.12. Okay, video's over. Bye.